In this video, we are going to learn about fitting a regression line and residuals. And the data set we're going to use as a very good example here has to do with the Billings Lee Health Center, which offers a regimented weight loss program for its customers. The program director monitored 83 men, and there's a file called BHC that contains data on the weight they lost after 6 weeks on the program, and the average daily calories each consumed per day. So we would like to see the relationship between the two variables, weight lost and calories consumed. Well, since both are numerical variables, we are going to start off with a scatter plot. And to do that, let's see the raw data set. So I'm going to pull up the raw data set. Here is the data set. I have calories and weight lost. I would think that the weight lost would depend on what calories consumed. So to generate a scatter plot, we can go to graph. There's scatter plot here. But I will recommend that you go to statistics, go to regression, go to simple linear regression, and in particular, our x variable is the independent variable, and our y variable is the dependent variable or response variable. I'll assume that in this case, we want weight loss to depend on what? Calories. So in this case, we want weight loss to depend on the calories taken in. Next step would be leave the perform. We're going to need this detail for the intercept and the slope. You'll soon understand what that means in a little bit. And in particular, we would like both to keep things simple for a start, we would like the residuals and the predicted values. So here we go. We're going to compute this. And you will notice that we have two new values. We would understand what this means, but for the meantime, I'd like us to focus on the second pane here, which is the scatter plot. So I have that scatter plot already posted here. Remember, for a scatter plot, we'll need to talk about the direction. In this case, this would be negative. So we have a negative relationship here. And the form is linear. I can see that most of the points are closely clustered together. So I'll say reasonably strong. Remember, this can be measured objectively using the sample correlation coefficient, and they're so reasonably strong. And if I'm in doubt, I can always compute the correlation coefficient. And you might notice that if you go back to the first page here, we have the correlation coefficient here, which is negative 0.97. That is extremely strong, very close to -1. So, as it is, I can say very strong or reasonably strong. And for outliers, I would say no outliers. So I'm going to put all of this together in words, and I would say that to describe the type of relationship that exists between the two variables, that weight loss, weight lost, and calories appear to have a positive, oh, excuse me, this should be negative, a negative from what we did earlier, a negative, linear, and very strong, in fact, rather than say reasonably strong, let's say very strong association with no extreme outliers observed. Then part B, pertaining to the very strong, how do we know that? We can use our R to get a numerical measure or a numerical statistic by computing the correlation coefficient for this sample data, which we got to be negative 0.97 from our earlier analysis here. And going back, what does that mean? This means that weight loss and calories have what? Have a very strong negative linear association. Okay. The next part of our analysis is to look at what percentage of variation in weight loss can be explained by the average what calories consumed. What this means is that in order to predict how weight loss will vary from one person to another, how much information can we count on average calories to provide as far as this sample data is concerned? In other words, this is otherwise called the coefficient of determination, and it is equal to your correlation value squared. The good news is in StatCrunch, the result we have provided that value, which is your R squared, that is 0.95 taken to 2 decimal places. So you have 0.95, same as 95%. This represents the percentage of variation in weight loss that can be explained by calories consumed. In other words, calories consumed holds what? A significant portion of what? The information we need to explain why weight loss varies from one person to another. Now, we've talked about the fact that this is a linear relationship. If it is linear, then it should have the form y equals mx plus b, the equation of a line. So, can we find the slope of that line and the y-intercept? Well, using technology, we can find it. We're later going to talk about how to compute it by hand. So let's go back to StatCrunch. I can see that this is my y equals, this is my m, and this is my x, m beside x, and then my b is 133.49297. So I have this equation, and I've brought it over here. So predicted weight loss is the intercept. This is my slope, my y-intercept. This is b, and this is my m, and this is my x. Now, our interest next is these numbers that I've highlighted, the yellow number, can we interpret it? These are the model estimates or the regression parameter estimates. Well, this negative 0.062148 is negative, which means that an increase in one will be associated with a decrease in another. That is not surprising given the negative relationship between weight loss and calories consumed. So we know that as one is increasing, the other tends to be decreasing. So the interpretation of this value then is that for every unit increase in your X, that is, in calories consumed, we estimate that the weight loss will be associated with increase here. Since this is negative, it will be associated with a decrease by as much of as 0.062148 in units of what? Of weight loss. Okay. Now, with that said, we have seen how to generate the model, how to look at our coefficient of determination, and how to interpret that too. But we do have an intercept here. Does it have a meaning? Well, what we do is that, you see, when calories consumed is equal to 0, that is, if we set this value to 0, 0 multiplied by this will give us 0, and 137.49 minus that 0, you have 137.49. That will be the weight loss, the predicted weight loss. So we're saying that for those consuming 0 calories, the amount of weight they will lose is 137.49 pounds, or whatever units weight loss is. So as it stands then, we ask, is this practical Is it practical that a person will consume zero what units? Maybe if they're fasting. So if it is practical, then the intercept has what practical significance. But if setting calories or your x equals zero, if it is not practical, then the intercept has no practical relevance. All right. Does the data provide strong evidence that an increase in what calories is associated with a decrease in weight? We have to test this claim. To test this claim, we set up the null hypothesis regarding the slope. If the slope is equal to zero, it means that 0 times calories, it nullifies the effect of the calories. It means that the relationship is not significant. So relationship between the variables, let's just keep that simple. Relationship is not strong enough or not significant versus the alternative that the slope is not nothing. That means it is something. So that means that the relationship is significant. How do we test this? What we'll need to do is go back to StatCrunch, and I'm going to go back to my options and edit. In this case, I already have my x variable in place and my y variable in place. I'd like to perform a hypothesis test on the intercept and the slope. These will be performed simultaneously, and I can compute again. And you will notice a couple of things, that in particular for the slope, I have a p-value here, which is extremely small, so small that it is smaller than what? 0.0001. So, as it stands in this case, I can say that p-value is very small, smaller than 0.001, which can be smaller than our level of significance, which is 0.05. Recall, when the p-value is less than alpha, what do? We reject the null hypothesis in favor of the alternative, which indicates that the relationship is significant. All right, very important to note. The next item we would like to discuss is the residual. The residual is defined as the actual value of your response variable minus the predicted value based on the regression model. So this was a sample regression model, and it is otherwise called the prediction line because it can be used for predicting the weight loss, which is why I have this at on top. This means predicted weight loss based on the number of calories consumed. So note that when you make predictions, it might not be exactly equal to the actual value. When that is the case, we define the residual for a particular observation to be the actual value of the response variable minus the predicted value. Okay, and how do we find that? The good news is if you have your data set, you'll see the predicted values here and the residuals. I have run this twice, which is why it is generating it twice. So this means that if I plug in 2053 into the regression model right here, 2053, multiplied by this slope plus the intercept, 137 point this, I'll have a predicted weight loss of 9.9. Notice that 9.9, what is predicted, is different from the actual weight loss, which is 10. So the residual in this case will be actual value 10 minus the predicted value. That will give me this residuals. Why are residuals very important? Notice that the smaller the residual, it is an indicator that what you predicted is what? Close to what the actual value is. In other words, we like our residuals to be really small. And residuals also have a very important quality. The sum of the residuals should be reasonably close to zero. In fact, so that means that the mean should also be very close to zero. So if I went to statistics and I want summary stats for columns and I want for the residuals, and if I want the mean, usually let me see if we have a sum. Yes, we have a sum right here. And let's compute that. You see that this is extremely small. This is 0.000000, almost 11 after what? The first zero. So you have 12 zeros in all. And that is literally zero. So that the sum of all the residuals is zero. Okay, so as it stands, we have the sum of the residuals being equal to zero. Now, sometimes if you look back at the residuals, some are positive, some are negative. Well, when do you have a positive residual? It is when the predicted value is smaller than the actual value. So in this case, we are under predicting. So positive residuals mean under prediction, whereas negative residuals mean over prediction, because what was predicted is more than or over the 10 that it actually is. All right, so that is what I'm explaining here. So when you have underestimation or under prediction, then the residual is what? Is positive under prediction. And when otherwise, when you have over prediction, the residual is negative. The residuals are very useful in evaluating how well a linear model fits your data. And that makes intuitive sense because the smaller they are, the closer your predictions are to the actual values. All right, so we have computed what the residuals for each observation in the data set using StatCrunch. And we have discussed why some of those residuals are negative. That will be the case where you have over prediction or overestimation, and others are what? Positive if you have under prediction. We also noted that the sum of the residuals is equal to what? Zero. Very, very near zero. Okay, let's see an example here. Residuals are helpful in evaluating how well a linear model fits a data set. The diagram below shows some sample data with their best fitting lines. So let's see if you have your y versus x, y versus x, y versus x. We might argue, or we might make a case for the fact that a linear model is a good fit for the first data set 1, 2, maybe for 3, it is really weak. But if we're in doubt, we can plot what we call a residual plot. For every residual plot, you're plotting the residuals versus the x variable, or the predicted values, For simplicity, let's say you're plotting the residuals versus x. And let us go to StatCrunch and let's plot the residual for residual here versus the calories. So I'm going to go to graph and I want a scatter plot of the residuals on the y-axis versus x, the calories on the x-axis, and I would like to compute. You see that this gives a random scattering. If it gives us random scattering, this is an indicator that a linear model is a very good fit to the data set. So going back here, I can see the residual versus x here. This shows a random scattering. And because it shows a random scattering, it means that the claim that a linear model is a good fit to this data checks out, is correct. You see, on the other hand, I can see a pattern here. That tells me that trying to fit a linear model here, trying to fit a linear model to this data set is not justified. What about the third one? I can see a random scattering. This is telling me that it is not bad to fit a linear model here. So this is very crucial to note. So when you're in doubt as to whether a linear model fits your data set, try to fit the residual plot. And with that residual plot, you will be able to decide more closely or in more exact terms if a linear model is a good fit to your data set. Okay? So here we have an example that talks about using linear regression to predict possum head lengths based on their total length. Of course, looking at the two numerical variables, if we talk about the direction, I would say that this is positive. And for the form, a linear equation will be great. And for the strength, I can make an argument that most of these points are what? Close. So I'll say reasonably strong. And do we have outliers or not? I would say no, there are none. So I can put all of this together in a statement to say the relationship between head length and total length of what? And total length of possums appears to be positive, linear, and reasonably strong with no extreme outliers. The question proceeds to tell us that they found the equation of that line, y at equals 41 plus 0.59x. And using that prediction line or the regression model, whatever you want to call it, what would be the predicted head length when total length is 85? When the total length is 85, then the predicted head length using the estimated regression line is y at equals 41 plus 0.59 times 85. And that should give about 91.5. This is what is predicted. This is the predicted value. The next part of the question says, what is the residual for this prediction? We recall that residual is the actual length minus the predicted length. So in this case, let us assume that we were given the actual length to be 98.6. And what we had predicted using the prediction equation was 91.5. How far off is our prediction from the actual value? That will be about 7.1. Take note, this is positive residual. When we have positive residual, it indicates under what? Prediction. Okay, well, if we are in any doubt as to whether this line is a good linear model to fit this data set, what we learned previously is to plot the residuals versus your x values. And did you notice there is no particular what? There is no obvious pattern in the residual plots. What does that mean? It means that a linear model is a reasonable fit to the data set.